cone right here that's helps focus the light. And then the light from this direction goes straight down this ommatidia. Each one of these is called an ommatidia. So light from here goes straight down this one. Light from this direction goes straight down this one. Way over here, light from this direction would go straight in this one. You get, coming in from all different directions. So the reason these eyes work is because they only let light come straight down the ommatidia. And it has to be shielded by light-absorbing pigments that block out light from the side. See, light from here, if light from here came in, it wouldn't work, right? The fly's brain takes all these inputs, these little optic nerves, bundle of axons going to the brain, and the fly's eye computes it and creates an image. So you have to shield these ommatidia with something that'll block out the light. So you need something that'll absorb the light, obviously, and that's what these pigments are. So let's say this. Each ommatidia is lined with tacked with pigments that absorb light and block it out. So it only goes straight down each ommatidia. So there's many, many pigments. With me so far? This all makes sense? Alright, so now let me show you what these many pigments are that have evolved. Okay. There are two sets of pigments in the fly's eye. One set are called homochromes. Chrome is a word for light in Greek. And these are brownish pigments. Now, this is a nice picture that shows what's going on. See, these are the homochromes, and here's one of them. It's the homochrome called xanthomatin. Got a benzene ring here, and a 3-carbon unit hanging off, carboxylic acid group, amine group there, and so forth. Remember that double bonds absorb light.
Double bonds absorb light.
Okay, lots of double bonds here. And this is synthesized, this molecule is synthesized in a series of enzymatic steps. Remember what enzymes do? Act like hands. They're protein machines, grab other molecules and construct them step by step. Each enzyme carries out one step like a series of workers on an assembly line in Detroit. Okay, the way you make this molecule is you start with 2 molecules of the amino acid tryptophan. Here's one. There's a second copy, same molecule. I'm showing one in black and one in orange so you can see how they make the final molecule. The enzyme known as tryptophan pyrrolase breaks the ring right here, breaks this 5-membered ring, see how it's broken? And you make a molecule called kynurenine. And then another enzyme coded by a different gene in the DNA takes the benzene ring here and adds an OH group onto it. It oxidizes the molecule, adds oxygen right there, OH, and that's called 3-hydroxykynurenine. And then another enzyme here that they didn't name, unfortunately, takes... see, the same thing's happening here. See, it's in parallel. And then you take 2 of these and put them together like this. Enzyme does that. That's hydroxoxanthomatin. And then still another enzyme takes off, converts this OH group to a carbonyl group, double bond O. And now you have xanthomatin. Now the point here is that each enzyme carries out one step in this biosynthetic pathway. And if you knock out, if you mutate the gene in the DNA that codes for that enzyme, what's going to happen? You can do this much, right? But you can't do this step, so everything downstream of here would be knocked out. So these would be genetic knockouts if you mutate the gene for each.